So in this video, we are going to try to prove Stokes theorem, which relates the circulation or the line integral of a vector field around any loop to the surface integral of the same vector field around a surface which is bounded by that loop. So to that end, let me first of all draw a loop, and even before that, let me draw the x and y axis and say here is our loop. The loop is supposed to be infinitesimally small. The loop is centered around the point x comma y. So this point here is xy, and the vector field we are considering, the vector field whose circulation we have to find around this loop, that vector field, say, is given by this. F of x is the x component of the force vector or the f vector, not necessarily the force, and f of y is the y component of the f vector. You can see here that both fx and fy are functions of x and y, that is the coordinates. So the vector varies from point to point. The vector f varies from point to point because from point to point these functions they give us different values at different x and y's. So therefore we have this vector field, and we have to find the circulation of that vector field around this loop, and we go around the loop in a specific way. In this example, say we go around the loop in this particular way, and let us say, let's call this line 1, let's call this 2, let's call this 3 and 4. We are considering the loop to be infinitesimally small, and this side, say, is just delta x and this side is delta y. So delta x and delta y are actually very small, and we have to find the line integral of the vector field f around this path. So this simply becomes f dotted with dr along 1 plus f dotted with dr along 2 plus the same thing along 3 plus the same thing along 4. Now, this seems a bit redundant to use integration just for a small loop, because usually we use integrations for adding up things over large portions of space. But in this particular case it is necessary, and we'll see that these specific integrations, they will come down to smaller expressions. So first of all, let us find out f dot dr over the line segment 1. Along the line segment 1, we can see that x changes from x minus delta x over 2 to x plus delta x over 2, while y remains constant at y minus delta y over 2. You can take a moment to see how that is. If the center point is x, then here along this entire line x is just x minus delta x over 2. Along this entire line x is just x plus delta x over 2. If the center point is y, the y coordinate of the center is y, then along this entire line y is constant at y minus delta y over 2, and along this entire line y is constant at y plus delta y over 2. So if we do the first integral, that is if we do f dot dr over this entire line, because delta x is very small, we can assume that f is constant, or if f is constant over this entire line, then obviously fx and fy, that is the x component and the y component of f, they are both, we can assume them to be constant over this line segment. So to that end, if we try to find this out, we can say it is just f of x at the point we are assuming that fx is constant over this entire line, and we are taking that constant to be the value of fx at the center of this line. So that just becomes f of x at x comma y minus delta y over 2, and the length of this line is just delta x. So the center of this point is x comma y minus delta y over 2, and the value of fx at this point, we assume that is the value of fx throughout this line. In the same way, if we find out the third integral, that is f dot dr over the line segment 3, then that will become, first of all, we'll have a minus sign because fx by definition is along the positive x-axis, that is I cap. So we have f of x at x comma y plus of delta y over 2, and we'll have to multiply that with delta x. So the first and the third integrations are done. Before we move on to the second and fourth, let us first see what this yields us. So what we can do is we can divide the entire expression by delta y and then multiply with delta y. So f of x at x, okay, I'll write it in a slightly different way. I'll take a negative sign common. So this becomes plus and this minus. So f of fx of x comma y plus delta y over 2 minus fx of x comma y minus delta y over 2. We have a minus sign out in front, divided by delta y and multiplied with delta x delta y. I hope you can see that this is just the definition of the partial derivative of fx with respect to y. So this is just the rate at which the x component of f changes with respect to y. So this is just delta fx with respect to y times delta x delta y. Now we could have found this out in a simpler way. For that, we can say this integral is just fx along the side 1 multiplied with delta x, and this would have become minus f of x along the side 3 multiplied with delta x, and this could have been written as minus fx along the side 3 minus fx along the side 1 times delta x. But what is this difference, fx along 3 minus fx along 1? For that we can use the approximation formula. So fx at 3 can be written as fx at 1 plus the rate at which fx changes with respect to y times delta y. So the value of fx here is just the value of fx here to the first approximation, but to the second approximation it is the rate at which fx changes with respect to y, because in going from fx1 to fx3 only the y has changed, times delta y. So the rate at which fx changes along y times delta y plus fx at 1 gives us fx at 3. But where do we have to evaluate this derivative? We have to evaluate this derivative at any point along this line, because we have assumed that delta x is very small, so fx has been assumed to be constant along this line. So if we assume that fx of 1 is the value of fx here, then this derivative is actually the derivative of fx with respect to y at this particular point. But that does not matter, because ultimately we let both delta x and delta y go to 0. So all the derivatives will eventually be evaluated at the point x comma y. So fx of 3 minus fx of 1 is just equal to this. So this expression becomes minus of delta, or the partial of fx with respect to y, times delta y. These two are the same. So for the second and the fourth integrals, I can either use this or this. I'll rather use this because this is a little smaller. So we can say that the sum of these two integrals, that is along 2 and along 4, that becomes f of y along 2 minus f of y along 4 all times delta y. I hope you can see that the integral along 1 and 3 doesn't have any fy in it, because we have done a dot product. So we'll have to use that component of f which is along that line segment. In these two cases, that is fx. In these two cases, it is fy. And here's a minus sign, because by definition fy is along positive y-axis j cap, while we are going in the downward direction. So in the dot product we get a cos 180, which leads to a minus 1. So in a very similar way, we can say that f of y at 2 is f of y at 4 plus the rate at which fy changes with respect to x times delta x. So fy here equals the fy here to the first approximation, but to the second approximation there is another term, which is the rate at which fy changes as we move along the x-axis times how much we have moved along the x-axis. So this becomes simply delta fy over delta x times delta x delta y. So we have this entire line integral. What that line integral amounts to, we shall see now. So the line integral of f dot dr along our closed path, let me see what we had got. It is delta fy with respect to x minus, the partial of fx with respect to y times delta x delta y. Delta x delta y is just the area of the loop. So delta x times delta y is the area of our loop, and this integral is the sum of these two terms, which I have written here. Now you'll have to note that this expression that we have got, this equation that we have got, only holds for the small loop for which this expression was derived. This is the small loop. Now if we want to go from this small loop to a bigger loop, then we can assume that that bigger loop is made up of many small loops. So if the line integral is done along every smaller loop, we'll see that the terms that are in between, they will cancel each other out. So this and this will cancel, these two will cancel, these two will cancel, these two will cancel, and ultimately this the left hand side of the equation will give us the line integral along the periphery of our of the surface that we are considering. The right hand side, if you notice a little closely, you will see that this is the z component of the curl of f, and this is just the area. So the z component of the curl being a vector, has been multiplied with the area, and the area, if we consider the area to be a vector, is actually along the z-axis. If you go back to the diagram, delta x and delta y, they were both in the xy plane. Our area was in the xy plane, so the area vector is along the z-axis. So the z component of the curl of f has been multiplied with the area vector. So that is simply the curl of f dotted with the area vector, because in the dot product we'll take that component of curl which is along the area vector. So our expression for the small loop is this. Now if we go from a smaller surface to a bigger surface, and in the entire surface, if we figure out this and this for every elementary loop and add them all up, this expression will become the line integral of f along the periphery of our surface, and this has to be evaluated for every elementary surface. So this ultimately becomes a surface integral. So this integral has to be done over the entire surface. So our expression for the bigger loop, the loop which is not infinitesimal but has finite lengths and breadths and everything, is ultimately this. You will also have to note that this surface can be any surface which is bounded by this loop. It doesn't, so if this is our loop, it doesn't necessarily have to be the surface which this loop encloses. Our surface may be a surface which is like this, maybe like a upside down hat or whatever. So the surface that we are considering here has to be bounded by the loop. We'll have a lot more to say about Stokes theorem when we discuss conservative forces and non-conservative forces, but let us end the video for now.